The goal of the next sequence in our lectures on the derivative is going to be to find derivatives for the exponential and logarithmic functions. To do that, we're going to need the definition of E that you see here, and it's going to take us a few theoretical steps to get there. Now, if you're following along with the theoretical side of the lectures, then you're in the right place. If you're just interested in practical matters and you're willing to accept this limit at face value, then you can skip ahead to the next presentation. Now, when I was an undergrad, sometimes professors it felt like they'd take off on a tangent and spend most of the class doing what seemed to be random things only to bring them all together in a flourish at the very end, like a magician pulling a rabbit out of a hat. And I always hated that since it made it hard to appreciate the big picture. So before we go any further, I want to give you a high-level view of what we're going to be doing. So I've got two sequences here, one of which, the first one, is identical to what I proposed for our definition. Now, to prove that that limit exists, and fundamentally, that's my goal here, to show that that limit exists, I'm going to do three things. First, I'm going to prove that this sequence is strictly increasing. That is, a sub n is less than a sub n plus 1 for every n. Then I'm going to prove that this sequence is decreasing, which is the opposite. Right now I'm going to show that b sub n is greater than b sub n plus 1 for every value of n. All right, that's the second thing. Now the third thing is going to be to show that the a sub n's are greater than the b sub n's for every value of n. In other words, b sub 1 is bigger than every value in that a sequence. And once I've accomplished that, I'll be done, right? Because if this sequence, the a sub n sequence, is strictly increasing and it has an upper bound, then it has to have what's called a least upper bound, and that least upper bound is going to be the limit. So before we go any further, we're going to need this inequality here, first proved by one of the famous Bernoulli family. And this is an example of how mathematics can be kind of modular in nature. I could have just incorporated this proof into the later ones when I needed it, but it's easier to prove this piece in advance and then just reference it when we get to the point of the other proofs where we need it. All right, so let's talk through what this statement is saying. There are a lot of similarities here. First, they both require a has to be greater than -1, and they both require n has to be an integer. All right, so the first one says, if a is not equal to 0 and n is greater than or equal to 2, then this inequality is true. And the second one is a looser statement. Now, it's okay for a to be 0. I didn't take that out here. And a can be any non-negative integer. So that's going to include 0 and 1, which weren't included up in the first statement. And if I want to include 0 and 1, I have to lighten up a little on the inequality. You notice this is slightly different. It's greater than or equal to instead of strictly greater than. Okay, so here's how I'm going to prove this. I'm going to do this using something called mathematical induction. And if you've never seen this technique before, you're in for a treat, because this is a nice one to have in your toolbox. The way this works is we start by showing just very manually that the statement is true for n equals 0. Sometimes we'll do n equals 1 also. Sometimes if it's not true for n equals 0, we'll start at 1. Okay, then here's the induction part. I'm going to assume it's true for n and show that it's true for n plus 1. And if I can do that, then I know that it's true for every integer value of n, right? And here's why, right? If I know that it's true for 1, then I've shown it's true for 1 plus 1, which is 2. But if I know it's true for 2, then I've shown it's true for 2 plus 1, which is 3. And so on. 4, 5, Whatever integer you need, you will eventually get to it in this chain. All right, so here's what I'm going to do. I'm going to start by showing that the statement is true for 0 and 1. Right? Because if I do it for 0 and 1, then that kind of manually covers the two cases that make this second statement different from the first. All right, then I'll show that it's true for n equals 2. Then I'll do the induction bit. All right, so when n equals 0, what do we have? Well, the inequality is 1 plus a to the 0 is greater than or equal to 1 plus a times 0. Now, do you see why I didn't want to let a be -1? If a was -1, then that left side would be 0 to the 0 power, and that's undefined, right? So that's kind of why we want to stay away from that particular number. So now if we simplify this, what do we get? Well, 1 plus a to the 0 is 1, and that is greater than or equal to 1. Excellent. The inequality works. Now let's show it for 1. When n is equal to 1, we get 1 plus a to the first, which is greater than 1 plus a times 1. Well, the left side is 1 plus a, and the right side is 1 plus a. So, yes, that is greater than, it's not greater than, it's equal to, right? Now, do you see why we had to slip equals in, right? For these two small numbers, I had to allow equals to happen for the statement to be true. Now, when we get up to 2, we can tighten things up, right? And we're able to do a strict inequality. So, let's see this for n equals 2, right? If I put 2 in here, this is 1 plus a squared. That's the left side. Now look, let's multiply this out. This is 1 plus 2a plus a squared. Now, because any number squared is positive, and because we have this one little requirement here, right, a can't be 0. That means that a squared is strictly greater than 0, which means if I take it away, I make the resulting number, the resulting expression, smaller. Right? So this has to be greater than 1 plus 2a, but that's what I needed to show. Right? If you replace n with 2 here and 2 here, you get that inequality. Right? So now I've shown the two special cases, 0 and 1 work, and I've shown this works for n equals 2. Now I'm going to do the induction part. Right? So I'm going to assume that 1 plus a to the n is greater than 1 plus an. I need to show that if this is true, then if I replace n with n plus 1, it's also true. So let me write that up here just so we know what we're aiming for. I want to show this, greater than 1 plus a and plus 1. All right, so let's see. What is 1 plus a to the n plus 1? All right, look, I'm going to split this up. I'm going to make this 1 plus a to the n times 1 plus a. I mean, that's fair, right? Now, look at what I assumed, right? Because I assume this is true for n, then this is greater than this. Okay, good. So let's do that. This must be greater than 1 plus an times 1 plus a. All right, excellent. Let's multiply this out, right, and see what we get. This is greater than 1 plus a plus an plus a squared n. Now I'm going to factor out an a from these middle two terms. This is greater than 1 plus a times 1 plus n plus a squared n. All right, well, a squared times n is a positive number, right? So if I take this away, the result is even smaller. So this is greater than 1 plus a to the 1 plus n. And that's what I wanted to show, right? That's what I was looking for. Let me bring this down here, right? 1 plus a to the n plus 1. And if you compare that to this piece right here, you'll see they are the same. That's what I needed to show. I showed that if it's true for n, then it's true for n plus 1. Therefore, we're done, right? That proves the inequality. Okay. Now, we're ready to get started on those two sequences. First, and I'm just warning you up front, this is going to involve a fair amount of algebra manipulation. So if you need to pause, and if you're taking notes, if you just need to stop and think through what each step, that's fine, right? Absolutely go ahead and do that. So here's what I want to do. I want to start by looking at a n plus 1 divided by a sub n. Right, and to do that, I'm just going to just use the formula, right? A n plus 1 is 1 plus 1 over n plus 1 to the n plus 1 over 1 plus 1 over n to the n. Right? That's just drop it in the formula. All right, now I'm going to do some common denominators so I can add these fractions together. I'm going to make this 1 into n plus 1 over n plus 1. And I'm going to make this 1 into n over n. Because now I can add these fractions together, right? This is n plus 2 over n plus 1 to the n plus 1 over n plus 1 over n to the n. Okay, now what to do next? Well, let's flip the fraction over, right? So I'm going to make this n plus 2 over n plus 1 to the n plus 1 times n over n plus 1 to the n, right? That's how we divide fractions, right? You flip the bottom one over and you multiply. Okay, so let's see. Now what am I going to do? Well, what I'd like is to, in a way, kind of combine these together. So I'm going to do something a little unusual here. Okay, I'm going to multiply the right-hand side times n over n plus 1, because that's going to make this part n over n plus 1 to the n plus 1. Then I can combine it together with that first one, but of course I can't do that. I'm going to balance this out by multiplying by n plus 1 over n, right? Because that whole thing there now is just 1, right? And I can multiply by 1 all I want. So now let's combine these two together, and this becomes n plus 2 over n plus 1 to the n plus 1 times n over n plus 1 to the n plus 1, still times n plus 1 over n. Okay, good. Now, let's see what to do next. I'm going to bring these two together. All right, I'm going to bring these together, right? Combine these two, and I'm going to go ahead and multiply them out. I'm going to do n times n plus 2. That's n squared plus 2n. If you're taking notes, leave a little space there. I'm going to add something in there in a minute. Right, and in the bottom, I'm going to multiply n plus 1 times n plus 1. So that's n squared plus 2n plus 1, still times n plus 1 over n. Now, here's what I'm going to do. right? And this is another one of these little weird algebra things. Just kind of bear with me. I'm going to add 1 here and subtract 1. Right? I mean, that's fair. 1 minus 1, that's 0. Right? I didn't change the number here by doing that. Right? So now, watch what happens. I'm going to split this into 2 fractions. I'm going to make it n squared plus 2n plus 1 over n squared plus 2n plus 1 minus 1 over n squared plus 2n plus 1 still times n plus 1 over n. Okay, good. Now, this piece here, that's just 1, right? So let's see. Let me write this out. This is 1 minus 1 over n plus 1 squared times n plus 1 over n. And somewhere along the line here, I lost my exponent. That should be n plus 1, n plus 1, and n plus 1. Okay, now, refer back to Bernoulli's inequality, right? Refer to Bernoulli's inequality because this expression here, right, the minus 1 over n plus 1 squared, that's between negative 1 and 0 whenever n is a positive integer. So that's going to be the a in Bernoulli's inequality, right? That's going to be the a. So this piece here is less than, let's see, that's going to be, well, excuse me, I got that backwards. I was looking at the inequality backwards. This is going to be greater than 1 plus 1 over, get that parentheses out of there, 1 over n plus 1 squared times n plus 1. This should still be a minus here. And we still have n plus 1 over n on the outside. Now, look at what happens here. We get some canceling inside the parentheses. This is 1 minus 1 over n plus 1 times n plus 1 over n. Now, let's do a common denominator here. Let's make this n plus 1 over n plus 1. Look at what's about to happen. Right? This is n over n plus 1 times n plus 1 over n, which is just 1. All right, go back to it. Remember what's on the left-hand side, right? The left-hand side was this expression over here. So what did we just show? We just showed that a n plus 1 over a sub n is greater than 1. Okay, we'll multiply both sides by a sub n. That's going to be fair, right? I can do that because a sub n is always positive, right? So I don't have to worry about the direction of the inequality. So this means a n plus 1 is greater than a sub n for all n. That's what I needed to show, right? That a sub n is an increasing sequence. All right, now for the other one. I need to show that this is a decreasing sequence, and it's going to be a very similar process. Right? It's going to be a very similar kind of algebra manipulation. So first, I'm going to look at the same thing. I'm going to look at bn over bn plus 1. And the formula here tells me that this is 1 plus 1 over n to the n plus 1 over 1 plus 1 over n plus 1 to the n plus 2. All right, common denominator, right? I'm going to add these things together, right? Let's make these 1s into n over n and n plus 1 over n plus 1. So now I can add these things together. So this is n plus 1 over n to the n plus 1 over n plus 2 over n plus 1 to the n plus 2. Okay, straighten out the fractions, right? I'm going to flip the bottom fraction over just like we did before. N plus 1 over n to the n plus 1 times n plus 1 over n plus 2 to the n plus 2. Okay, now once again, I want to combine these things together, right? And to do that, I need to give that n plus 1 exponent, I need to make that an n plus 2. So I'm going to do a very similar thing. I'm going to multiply by n plus 1 over n times n over n plus 1. Right, so let's see. Now I'm going to combine these two together. And this becomes n plus 1 over n to the n plus 2 times n plus 1 over n plus 2 to the n plus 2 times n over n plus 1. Right, so now let's combine these, right? And let's see, I'm going to go ahead and multiply it out, right, just like I did before. This becomes n squared plus 2n plus 1 over n squared plus 2n to the n plus 2 times n over n plus 1. Now, I'm going to split them, just like kind of like I did before, right? You notice I've got this n squared plus 2n on the top here. So I'm going to split this that way. I'm going to make this n squared plus 2n over n squared plus 2n plus 1 over n squared plus 2n to the n plus 2 times n over n plus 1. This piece here is just 1. And now it looks like Bernoulli again. 1 plus 1 over n squared plus 2n to the n plus 2 times n over n plus 1. Right? Now, this n squared plus 2n, this is in the place of the a, right? And you'll notice we also have to make sure those requirements are met. 1 over n squared plus 2n. This is always going to be less than 1, and it's always going to be greater than 0. So it is an acceptable a value, right, to apply Bernoulli's theorem. So what I know is this expression here, I'm going to write it off to the, see where I can squeeze it in. What do I know? I know that 1 plus 1 over n squared plus 2n to the n plus 2 is greater than 1 plus n plus 2, that's the exponent, times that a value, 1 over n squared plus 2n. That's Bernoulli's rule. Okay, so I'm going to make that substitution now. This means bn over bn plus 1 is greater than, let's see, what's it greater than? 1 plus n plus 2 times 1 over, I'm going to factor that thing. That's n times n plus 2 times still n over n plus 1. Look, we get some nice canceling here, right? So this is 1 plus 1 over n times n over n plus 1. And if I do a common denominator here, make this n over n, then this is n plus 1 over n times n over n plus 1. And look, the exact same nice thing happened. That's just 1. Right? Multiply both sides by bn plus 1, which is fair, right? Because the b's are all positive. So then I get bn is greater than bn plus 1, which is what I needed to show. The numbers are getting smaller. Right? They're getting smaller as we go along, which means this sequence is decreasing. All right, now I can show that these limits exist, right? And since we're at it, and that they're equal to each other. Okay, so I'm gonna start with this a sub n and b sub n. It's going to be the same the same sequences that we had on the previous two slides. Right now, first, b sub n equals 1 plus 1 over n to the n plus 1, which is the same as 1 plus 1 over n to the n times 1 plus 1 over n to the first. Right now, this 1 plus 1 over n to the first, that's a positive number. Right? So if I take, it's a positive number that's greater than 1. Right? So if I take this away, then the result becomes smaller. So this is greater than 1 plus 1 over n to the n, which is a sub n. All right, so what I've shown here is that b sub n is greater than a sub n. In fact, let me turn this around, because we usually do smaller than larger, right? So this means a n is less than bn for all n. Okay, but remember, b is a decreasing series, which means as I start doing smaller indexes, right, these numbers are bigger, right? The earlier numbers in the b sequence are the bigger ones. And with the a's, it's the other way around, right? A n minus 1 is less than a sub n, is less than a sub 2, is less than a sub 1. Right? So what this shows is the a sub n's are bounded. A sub n is less than b sub 1 for all n. Right? So what do we know? A sub n is an increasing sequence that is bounded above. That means it has a least upper bound, which means that our limit must exist. The limit of a sub n as n approaches infinity equals something, right? It equals a number, right? And by the exact same argument, when we're talking about the b's, b is a strictly decreasing sequence that is bounded below. Therefore, it has a greatest lower bound, so its limit exists. So the limit b sub n as n approaches infinity also exists. Okay, great. It's an important step. Now I know that my limit equals something. Okay, now I want to show that these two limits are the same. All right, here's how I'm going to do that. First, I try not to do this, but I really am out of room. So let me make some space. We'll get some room to work here. What I'm going to do is I'm going to look at the difference between these two sequences. Right, so I'm going to look at b sub n minus a sub n. All right, so what does this equal? Well, this is 1 plus 1 over n to the n plus 1 minus 1 plus 1 over n to the n. All right, now let's factor this. I'm going to factor out 1 plus 1 over n. All right, so that's going to leave 1 plus 1 over n from the first part and just a minus 1 from the second. Okay. Whoa, I lost an exponent though, didn't I? That's to the nth power. All right, so what is this? This is, let's see, this piece here is just 1 over n, right? So this is 1 plus 1 over n to the n times 1 over n. And this first piece here, well, that's just a sub n again. So this is a sub n over n. Okay, but remember, a sub n is less than b sub 1 for every n, right? Therefore, 0 is less than b sub n minus a sub n is less than b sub 1 over n, which equals, if you go back to the formula for b, substitute in 1 for n, you see that b sub 1 equals 4, right? So this is 4 over n. Okay, and that did it. Now we're going to apply the sandwich theorem or the squeeze theorem, right? The same name. I'm going to do the limit n approaches infinity of 0 is less than or equal to the limit n approaches infinity, whoops, got them in the wrong order, b sub n minus a sub n is less than or equal to the limit n approaches infinity of 4 over n, right? The left-hand limit here is 0. The middle limit stays the same, less than or equal to 0, right? So what does that mean? That means that the limit as n approaches infinity of the difference is 0. And then you use your limit rules, right? This is the limit n approaches infinity b sub n minus the limit n approaches infinity a sub n. Move that second limit over, add it to both sides, and we get the limit n approaches infinity a sub n equals the limit n approaches infinity b sub n. The two have to be the same. Okay, that's what I need to show. Right now, I've showed primarily I've showed that the limit n approaches infinity of 1 plus 1 over n to the n exists. It's finite. It's a number, and I'm going to call this number e. Right? That is our definition, our calculus definition for the base of the natural logarithm. Okay, and here it is again. So should have gone to the next slide before I started talking. Right? This is now going to be our working definition. All right. So what's next? Now that we've got this in hand, we're ready to talk about the derivative of the exponential function, which is really the calculus concept that we were driving toward. We just needed that. We're going to need that official calculus definition to show what that derivative equals.